The next slide shows the setup for pumping the rubidium gain cell. The first laser on the left is a neodymium YAG Q-switched pulse frequency doubled neodymium YAG laser, followed by in forefront in orange, that's a dye laser, and that's pumped by the neodymium YAG laser, and at the output, the beam is then steered by a series of mirrors towards the gain cell. And so this is the optical path. In the next slide, figure 8 shows the optical path after the 780 nanometer beam leaves the output of the dye laser, and it's steered towards a quarter wave plate using a series of beam steering mirrors. The quarter wave plate converts the linearly polarized light into circularly polarized light and vice versa. Wave plates are constructed out of birefringent materials such as quartz or mica, for which the index of refraction is different for different orientations of light passing through it. The beta of the wave plate depends on the thickness of the crystal, the wavelength of light, and the variation of the index of refraction. And by the appropriate choice of relationship between these parameters, you can introduce a controlled phase shift between the two polarization components of the light, thereby altering its polarization. The beam then passes through two focusing lenses and a polarization beam splitter, which sunlight gets reflected towards a beam dump or perhaps a photometer or optical power meter, and the rest of it goes through the rubidium gain cell itself, and after which it then hits a highly reflective mirror, and this process goes back and forth, and this section is called a resonator. As you will see in the next slide, the resonator section of the DPAL. Resonator section, the DPAL is placed in an oven and monitored for temperature, and the temperature kept at about 200 degrees Celsius. And this is the critical component, the gain cell. And this is where the atomic rubidium is heated to 200 degrees Celsius. So in the next slide on this particular experiment, the laser pumping of the rubidium gain cell, typically we try to measure the slope or efficiency, P out over Pn, and so on two different runs, with efficiencies as predicted are usually very high for this laser, and in run 1 we're looking at close to over 80%, and in run 2 over 90% efficiency. The next slide shows the optical damage phenomena in a rubidium ethane gain cell. Dissociation of ethane due to rubidium vapor. 20 kilowatt laser was fired into the booster angle entrance of the optical window, and the results are shown here, where there is optical damage, there is striations of the optical window, carbon from the dissociation of ethane deposited. And so this is an example of what happens in a rubidium DPAL. This is a quartz optical window, and so the purpose of the research is really to make sure the laser can scale to higher powers without being damaged, as shown here. Now we focus in on the rubidium DPAL gain cell. which is the portion of the DPAL of great interest to us, because the gain cell is filled with, in some cases, helium and the atomic rubidium at 200 degrees Celsius, and laser is pumped through the front window on the input pump side, 780 nanometer. On that side, we need an external anti-reflective thin film coated surface. So if we take a look at the optical window surfaces, we need the AR, or anti-reflective, to minimize losses of the input laser. Then on the opposite side, on the inside surface, we need an atomic rubidium damage-resistant optical thin film. So the gain medium typically contains helium and atomic rubidium at 200 degrees Celsius, and the 780 nanometer comes in and pumps at 3 levels to 795 nanometer at the output, and gets reflected on a high reflector on the back end of the optical window, and reflected back into the gain medium and out through the input pump window. So if we can make the thin film atomic alkali resistant, this would improve the optical window surfaces and their ability to withstand damage. The next slide deals with the front surface of the optical window of the DPAL on either side, and it's typically contains or is made of optical thin film, which is anti-reflective. So anti-reflective coatings, which are designed using the quarter wavelength technique to basically constructively, destructively cancel reflections, and will allow less than 1% of the incident laser beam to be reflected. So a lot of energy savings there by having almost 100% of the laser transmitted through without reflections. Typically, magnesium fluoride can be utilized. There are many different types of coatings that can be utilized for anti-reflective.